All right, let's continue. So one last remark about this example. So essentially, note that, okay, let's get started, please. So one final and important remark is the following. So if an LP problem is unbounded, that basically means that I can find feasible solutions whose objective function values are arbitrarily good, basically, right? So for example, this is a maximization problem, so which means that if the problem is unbounded, then I can, for example, find a feasible solution whose objective function value is equal to 1 million, for instance, right? So the question is, how can I do that? So for example, does this help me in finding a feasible solution whose objective function value is equal to 1 million? How can I use this result to actually show that there exists a feasible solution whose objective function value is equal to 1 million, using this derivation here? So essentially all I need to do is the following. I'm going to plug z equals 1 million here, and that's going to give me the corresponding value of a, which of course will be equal to 500,000 or 500,000. And if I put a equals 500,000, then that's going to give me the corresponding feasible solution, okay? So as a result, I mean, this also tells you to find feasible solutions with arbitrarily good objective function values as well, okay? If I want to find a feasible solution whose objective function value is equal to 1 billion, for instance, I can also do that, okay? So, in other words, the fact that the problem is unbounded essentially means that I should be able to find feasible solutions with arbitrarily good objective function values. And by using these equations, I can also do that. Okay? So, which means that if you ever come across a problem where the problem is unbounded and they ask you to find a feasible solution with objective function value equal to 10,000, for instance, you can also do that by using this formula. Is that clear? No. So what I'm saying is the following. By using this sort of derivation, this final result, this expresses the objective function value and the values of your variables in terms of the parameter a. Okay? And it's not too hard to see that if I simply let a go to infinity, then z will also go to infinity as well. Okay? So as a result, this implies that by making a larger and larger, the objective function value will be larger and larger. Okay? So that, which implies that the problem is unbounded, basically. Okay? So the objective function value can be made arbitrarily large. So what I'm saying is that since the objective function value can be made arbitrarily large, then I should be able to find a solution for any possible objective function value. Any large objective function value, basically. Okay? So which means that if I'm looking for a solution whose objective function value is equal to, let's say, 10 million, I can do that by using this formula. Okay? All I need to do is I need to find out, well, for which value of a will z be equal to 10 million? Okay? And solve for a, and then plug a into this sort of system, and that will give you the corresponding values of x1, x2, x3, and x4. Okay? So you can also use these sort of results to find feasible solutions whose objective function values are arbitrarily large, basically. Is that clear now? All right. So, any questions before I move on? Yes?
If you think that as a real-life problem, so what does A correspond to? I mean, let's say the x1 is labor and x2 is something else. Can we find something that is realistic for A?
Well, that really depends on the problem, the underlying problem. So this basically tells you that whatever the value of x3 corresponds to, by increasing that, I can make the objective function value larger and larger. So that's all we can sort of conclude from this example for now. Okay? But as I said, I mean, if this is a real-life problem, and if the problem is unbounded, that essentially means that probably there's a constraint that you should have added and you didn't add. So you should go back to your model and do something else. Okay? Because real-life problems usually are not unbounded. Okay? However, later on we're going to see that when a problem is unbounded, it gives us information about a different LP problem, and that's going to be useful as well. Okay? Other questions? All right. So if you recall, we talked about degeneracy right before we started discussing simplex method. And in 2 dimensions, there are some examples where there are more than 2 lines intersecting at the same point, right? So we have seen such examples. And we also said that, well, in such cases, we might have a problem because even if I change the sort of basic variables, I'm actually still getting the same corner point, right? So do you remember that example? Yes. Okay. So now I'm going to try to illustrate how such a case affects the simplex method. So this is example number 6. So now I'm going to talk about degeneracy. Here comes the example. So suppose I want to maximize 3x1 plus 9x2. And here are my constraints. x1 plus 4x2 is less than or equal to 8. x1 plus 2x2 is less than or equal to 4. And x1 and x2 are non-negative. Okay? So once again, we have two variables. Let me draw the feasible region. Let me start with the first constraint. So if x1 is 0, x2 will be equal to 2, which is somewhere over here. And if x2 is 0, x1 will be 8, which is probably somewhere over here. Okay? So it goes through these 2 points. So this is the equation corresponding to x1 plus 4x2 equals 8. So which one is the correct side? 0, 0 satisfies the inequality, so it's going to be basically the side that contains the origin, which is this side right here. So what does the second constraint look like? So if x1 is 0, x2 again will be equal to 2. Okay? And if x2 is 0, x1 will be equal to 4. So 4 is the midpoint here. So it's going to go through these 2 points. So this is a line corresponding to x1 plus 2x2 equals 4. Again, which side should I pick? Again, the origin satisfies the inequality, so I'm going to pick this side. Then I have non-negativity of x1 and x2. Okay? So what does my feasible region look like? So it's a smaller triangle, basically, right? So all right, so next I'm going to try to find the optimal solution. So I'm going to try to draw the line 3x1 plus 9x2 equals 0. I know it goes through the origin. I need one more point. So for example, if x1 is equal to 3, x2 will be equal to minus 1 exactly. So it's going to go through 3 and minus 1. And that actually looks like this point right here. Okay? And what's my C vector in this case? So it's given by 3 and 9. And 3 and 9 actually points in this direction. Okay? And since this is a maximization problem, that is the improving direction. So I need to sort of push the isoprofit line in that direction. And if you do that, you're going to see that the best solution will be over here. Okay, so this solution right here. Okay? And that solution is, I think, given by x1 is equal to 0 and x2 is equal to 2, right? Now, before I start, with the simplex method, so note that at this point, these 2 lines intersect, but this line also intersects, basically, right? So the line x1 equals 0, which corresponds to this constraint. So basically, there are 3 lines intersecting at the same point here. Okay? So there's a vertical line, which is x1 equals 0. There's this line and this line. So there are three lines intersecting at the same point. So which means that that corner point can be written as the intersection of 2 lines in 3 different ways, basically, right? So we have seen this before. So there are 3 lines. I need to choose 2 out of them. And I can choose 2 lines in 3 different ways, basically, right? Okay. So let's see if the simplex method will be affected by this. And I'm going to set up the tableau quickly. Again, I'm going to define x3 and x4 as the slack variables for first and second constraints. Now, what does row 0 look like? Again, just sort of negate all the coefficients in the objective function. So I can have -3, -9, 0, 0, and the right-hand side value will be 0. Then, what does the first constraint, or row 1, look like? 0, 1, 4, 1, 0, 8. So x3 is a slack variable for the first constraint. Then I have 0, 1, 2, 0, 1, and the right-hand side value is 4. Okay? So what are the basic variables? I have z for row 0. What's the basic variable for row 1? x3, and for row 2? x4, exactly. The non-basic variables are x1 and x2, so this is a basic feasible solution. What are the values of x1 and x2 for this solution? They're both 0 because they're non-basic. So this solution just corresponds to the origin, right, as usual. Okay? All right, so this is a maximization problem. What should I be looking for? A negative coefficient in row 0, basically, right? Because I want to increase the value of c. And do we have any negative coefficients in row 0? Yes, we do. We have 2 of them, basically. Okay? So I can either increase x1 or x2. Both of them will increase the value of c. But it seems like, increasing x2 will be better, right? Because it has a larger coefficient in absolute value. So I'm going to enter x2. So next I'm going to decide on the leaving variable. And for that I'm going to perform the minimum ratio test. Okay? What's the ratio for row 1? So 8 divided by 4 is equal to 2. And what about row 2? 4 divided by 2 is again equal to 2. Well, so what does this mean? Well, let me go back to my picture. So I decided to increase x2, which means that I'm going to start moving in this direction. Okay? And this is my first constraint. For the first constraint, the best I can do is this point. For the second constraint, the best I can do is, again, still this point, basically, right? Okay? So for both constraints, the largest value of x2, the largest value x2 can take is equal to 2. So I can never actually go beyond that. Now, which variable will be the leaving variable? So that's the next question. Well, can I make both of them the leaving variable? Why not? Sorry?
When we choose the leaving variable, we make it 1 and the line, all of them are 0.
Uh-huh.
On the same line, we have to do 2 ones.
Exactly. So, if you think about how the simplex method works, so every time it actually makes an iteration, every time it moves from one tableau to the next one, it makes one non-basic variable basic, and one basic variable becomes non-basic, right? So it basically replaces one of the basic variables with one of the non-basic variables. Okay? So as a result, there cannot be 2 leaving variables. Okay? There should be exactly 1 leaving variable. But now we have a problem because, both rows actually give me the exact same ratio. Okay? So just like we had a choice in terms of the entering variable, we also have a choice in the leaving variable here as well. Okay? So actually either of them can be the leaving variable. Okay? So what I'm going to do is, I'm going to actually pick x3 as the leaving variable. Okay? And I could have also chosen x4 as a leaving variable as well. Okay? So nothing would have changed, basically. However, let's say that, I decide on x3, so I'm going to pivot on this entry, right? So I'm going to look at the entering variable x2. I'm going to look at the leaving variable x3. And the intersecting element is 4, so I'm going to pivot on that entry. And let me do one iteration. So what's the first step? So I'm going to make the column underneath x2 look like the column underneath x3, basically, right? So I'm going to make this 0, 1, 0. So always start with the circled entry first. So I want to make the circled entry equal to 1, right? So how am I going to do that? So I'm going to divide by 4, and if I do that, I have 1 over 4, 1, 1 over 4, 0, and the right-hand side value is 2. Okay? Then I'm going to multiply the new row 1 by minus 2 and add it to old row 2. Okay? And if you do that, you end up with 0, 1 over 2, 0, minus 1 over 2, 1 and 0. Okay? And finally, I'm going to multiply this by 9 and add it to row 0, so that this entry becomes 0. Okay? And if you do that, you have 1 minus 3 over 4, 0, 9 over 4, 0, and 18. Sorry? Now let's again figure out the basic variables. I have z for row 0, that never changes. What's the basic variable for row 1? So I'm going to have x2. What's the basic variable for row 2? It's going to be x4. So now let's make some observations here, okay? So what are my basic variables? x2 and x4, okay? And what's the value of x2? 2. What's the value of x4? So we have a basic variable whose value is equal to 0, right? So what does that imply? So this implies that this is a degenerate basic feasible solution, basically, right? So since we have a basic variable whose value is equal to 0, this solution is degenerate, okay? So this is a degenerate basic feasible solution. Since x4 is basic, but x4 is equal to 0. All right, so what is the corresponding solution in my picture? What's the corresponding corner point? x1 is 0 and x2 is equal to 2, right? So what does that correspond to? Well, it's exactly this point right here, basically. Okay? However, if I look at this solution right now, and I know that this is the optimal solution, right? But if I look at this solution right now, there's still a negative variable here, right? Negative coefficient here. Right? So did we make a mistake? Well, no, we didn't. Well, essentially, this is a problem with degeneracy, okay? So the simplex method actually at this stage already found the optimal solution, but it hasn't realized that that's the optimal solution in some sense, okay? So if I look at this tableau, x1 is non-basic and still has a negative coefficient. So as a result, by the rule, I need to try to increase the value of x1, okay? So now x1 enters, okay? Now what's the leaving variable? Well, I'm going to look at the ratio. What's the ratio for row 1? 2 divided by 1 over 4. So that's equal to 8. And what's the ratio for row 2? 0 divided by 1 over 2. And that's going to be equal to 0. Okay? Now let's try to understand this again. So I'm trying to increase the value of x1 because I know that by increasing the value of x1, I can increase the value of z, right? Okay? And the ratio test tells me how much I can increase the value of x1. Okay? So from row 1, I know that I can increase x1 up to 8 if I want to still satisfy the first constraint. Okay? But if I look at the second constraint, it tells me that the best I can do is set x1 equals to 0. Okay? So I want to increase x1, but the largest I can increase x1 to is equal to 0. Okay? So which means that essentially, here's what's going on. Remember, row 2 corresponds to this constraint right here. Okay? So I want to increase the value of x1, so which means that I want to move along this direction. But the best I can do is actually stay where I am right now. Okay? So I want to increase the value of x1, but constraint 2 already blocks me immediately in some sense. Okay? So there's no way I can increase. So I want to increase it, but I cannot increase it more than 0. Okay? So as a result, what I'm going to do is the following. I'm going to just do the usual step. So x1 enters and x4 leaves, because x4 gives me the smallest ratio. Okay? So which means that I'm going to pivot on this entry. Okay? And let's see what we have. So I'm going to do one more tableau. So I have z, x1, x2, x3, and x4 on the right-hand side. So let me pivot on that circled entry. So first of all, I need to I need to multiply row 2 by 2, right? And if I do that, I get the following: 0, 1, 0 minus 1, 2 and 0. Then I'm going to try to make the other entries in the first column, well, in the column of x1 equal to 0. So I'm going to multiply this row by minus 1 over 4 and it to row 1. And if I do that, I end up with 0, 0, 1, 1 over 2, minus 1 over 2 and 2. And then I'll just multiply this row by 3 over 4 and it to row 0. Okay? And if you do that, you end up with 1, 0, 0, 3 over 2, 3 over 2. And the right-hand side value is 18. So what are the basic variables? I have z here. What's the basic variable for row 1? x2 is basic. What about row 2? x1 is basic. Now this is a maximization problem. Is that an optimal solution? Yes, it is. Well, if I look at the values of my variables, x1 is a basic variable, but its value is equal to 0. x1 was a non-basic variable, and its value was equal to 0, basically, right? x2 is basic, and its value is equal to 2. x2 is basic, and its value is equal to 2. x3 is non-basic, it's equal to 0. x3 is non-basic, it's equal to 0. x4 is basic here, and it's equal to 0. x4 is non-basic, and its value is equal to 0. So essentially, these two solutions are the same in terms of the values of variables, right? Okay. The only difference is that, here x2 and x4 are basic, and over there x1 and x2 are basic. Okay. So here, what is the corresponding corner point? Well, we're still exactly at the same point. We haven't moved at all, right? So we're still looking at x1 equals 0 and x2 equals 2. Right? We're still looking at the same solution, and over there x1 is equal to 0 and x2 is equal to 2. But the simplex method, actually, by doing a pivot from this tableau to that tableau, nothing has changed, actually, in terms of the values of my variables. Does everybody see that? Okay. The only thing that has changed is the labels of my variables. Okay. Here x4 was basic, and x4 is non-basic over there. Over there x1 is basic, and x1 was non-basic here. Okay. And note that the objective function value did not change either, right? So I start with 18, and over there I still have 18. Well, this solution is not optimal, but that solution is optimal. Okay? Well, this is basically what happens when there's degeneracy in the problem. Okay? So, for example, in this case, first of all, the simplex method already finds the optimal solution at this stage, but it cannot detect that it's an optimal solution, so it has to do one more iteration, and it actually sort of finds that tableau, and from that tableau it can say that it's optimal solution. Okay? However, at this tableau, despite the fact that this is already optimal, the simplex method cannot yet tell if it's optimal or not. Does that make sense? Okay. Secondly, the fact that the value of z has not changed should not be surprising, actually, for you, because I'm trying to increase the value of x1, but the best I can do is keep x1 equals 0. Okay? So, which means that if x1 was 0 here, and x1 will be 0 in the next solution, which means that the value of z, of course, will not be affected in the next solution. Okay? And indeed, the value of z is still equal to 18. So nothing has changed. Okay? So this is exactly the same situation that we had earlier in our earlier example. So if I use my basic variables as my basic variables x2 and x4, and if I use as my basic variables x2 and x1, I'm still looking at the same solution. Okay? In other words, this corner point is represented by different sets of basic variables. Okay? I change my basic variables, but my corner point does not change. Okay? So this was a problem that has never happened in the previous examples, because in the previous examples, whenever I change my basic variables, I always move to a different corner point. Let me repeat that again. So in the previous examples, whenever I change my basic variables, I always moved to a different corner point. Okay? So here, essentially, this is what degeneracy means in some sense. So the simplex method is trying to move, but it cannot move anywhere at all. So it's actually stuck at this solution. Okay? So it's taking this solution, it's representing it by these basic variables, and representing it by these basic variables cannot tell the simplex method that this is optimal. So what the simplex method needs to do is, it has to change the basic variables for the same solution, and only by using a different set of basic variables can the method tell us that this is optimal. Okay? So in other words, the simplex method actually is doing a step without making any improvement, in some sense. Okay? I mean, one way to see this geometrically is that you want to move from this point, but you're stuck, basically. Okay? So you want to move, but you're immediately stopped by the second constraint. Okay? So this has never happened before because in the previous examples, all the corner points actually was precisely given by the intersection of two lines exactly. Okay? So which means that in that case, whenever I change my basic variables, I always make sure that I move to a different point. Okay? Whereas when there is degeneracy in the problem, then we have this situation. Note that that's also a degenerate basic feasible solution, right? And despite the fact that the solution, the values have not changed, actually this is an optimal solution. Okay? So once again, I mean, when we think about this is the simplex method actually wasted some effort from going here to here. Okay? The objective function did not improve, but from this solution, the simplex method couldn't tell you that this was an optimal solution. Does everybody see that? So that's important. So as a result, we had to do one more iteration to actually make sure that this was indeed an optimal solution. So that's essentially what we do over there. Okay? So which means that whenever there's degeneracy in the problem, you may actually encounter such a situation. Okay? So you may actually do a simplex iteration. You may start with a tableau and go to the next tableau without actually making any real improvement in the objective function. Okay? Yes?
Bir corner point'tan bir diğerine götürüyor ya.
Hı hı.
Bu noktada üç ayrı line kesiştiği için yani bir ikilinin kesişiminden bir diğer ikilinin kesişimine götürüyor ama onlar aynı nokta oldukları için güzel yerde kalıyor.
Exactly. Exactly. That's exactly what's going on. So, as I said, it's first representing this corner point by these basic variables. Then it's representing the same corner point by a different set of basic variables. Okay? So since this point can be written as the intersection of two lines in three different ways, this is one possibility, that's another possibility basically, okay? So that's the reason why, despite the fact that your basic variables are changing, your solution is not changing, because you're still looking at the same corner point. Okay? Other questions? So let me then give you some remarks, because this is important. So remember the definition. A basic feasible solution is corresponding to a simplex tableau. Tableau is degenerate if the right-hand side value of at least one basic variable is equal to 0. So once again, when I talk about basic variables, I'm just looking at original decision variables. I'm not talking about z. Okay? So I'm not really considering z as a basic variable. My basic variables are x3 and x4. For instance, this is a degenerate solution because x4 is basic and its value is 0. That solution is degenerate because x1 is basic and its value is equal to 0. Okay? So C, BFS 2 and 3 in the previous example. So the second basic feasible solution and the third basic feasible solution will be degenerate. So the second observation is the following. Note that the values of all the variables are the same. All the variables are the same in BFS2 and BFS3, so which are the second and the third basic feasible solutions. But the basic and non-basic variables are different. So in other words, different sets of basic solutions, different sets of basic variables, represent the same corner point. So this was a situation that we have already seen in the previous examples before we started discussing simplex methods. So I'm changing my basic variables, but I'm still looking at the same corner point. Okay? Now for this one, this is really important, so I just want you to pay attention to me for a second. So the minimum ratio, the ratio for row 1 is equal to 2. Okay? And the ratio for row 2 is also equal to 2. Okay? So what does this mean? So basically this means that if I want to satisfy the first constraint, then the best I can do is increase x2 up to 2. Okay? And note that when x2 is equal to 2, the value of x3 is equal to 0 basically, right? Because of the first constraint. Remember, x1 does not change, so I have 4x2 plus x3 is equal to 8. Okay? And when x2 is equal to 2, x3 has to be equal to 0. Right? So that this is satisfied. And if I make x2 larger than 2, then the value of x3 has to be negative basically, right? Okay? And the same is true for this one as well. So when x2 is exactly equal to 2, x4 has to be equal to 0, so that this is satisfied. And if I want to increase x2 further or more than 4, then the value of x4 will be negative. Okay? So which means that when x2 is equal to 2, both x3 and x4 will be equal to 0 basically, right? Okay? And indeed, if I look at the next solution, x4 still is basic, but its value is equal to 0. Okay? So essentially, in the first tableau, we had a tie in the minimum ratio test. So a tie basically means that there was more than one variable, one row, achieving the same minimum ratio. Okay? So in this case, both row 1 and row 2 had the same exact minimum ratios. So let me just use MRT for short. If MRT is achieved by more than one row, then the next basic feasible solution is always degenerate. And if you think about this a little bit, if you look at, again, the first tableau, both of them tell you that, remember the sort of the idea behind the minimum ratio test. So this is the largest value the entering variable can take before the corresponding value is negative, basically. Corresponding basic variable is negative, okay? So which means that when x2 is equal to 2, x3 has to be equal to 0, so that this is satisfied. And if x2 is larger than 2, then x3 has to be negative, basically. Okay? So I don't want that, so as a result, the best I can do is increase x2 up to 2, and the same is true for this one as well. So which means that, if I increase x2, x3 will decrease. If I increase x2, x4 will also decrease. But when x2 is exactly equal to 2, both of them will decrease to 0 at the same time. Okay? But one of them has to stay in the basis. Okay? One of them has to be a basic variable because I can only have one leaving variable. So as a result, whichever variable stays in the basis, which is x4 in this case, will have value equal to 0. Okay? So this is true in general as well. So if the minimum ratio is achieved by more than one row, then both of the corresponding values will be equal to 0 if I increase the entering variable. Okay? So as a result, whenever I have a tie, such as this one, okay, then in the next tableau, I should always have a basic variable whose value is equal to 0. Does that make sense? Okay? So as a result, whenever you apply simplex method and whenever the minimum ratio test is achieved by, minimum ratio is achieved by more than one row, that implies that in the next solution, you should have at least one basic variable which is equal to 0. And in that case, of course, the next tableau will be degenerate, basically, okay? Is this clear? This is important, so I just want to make sure that this is understood. All right, so any questions? Now, what does this mean? Well, essentially, whenever degeneracy is present in a given LP problem, then the simplex method may have some complications. So this is the main message. I mean, in this case, as I said, we had to do this extra step without making any improvement. And we already found the optimal solution in the second tableau, but the simplex method couldn't tell us that it was an optimal solution. It had to do one more step to realize that this was an optimal solution. Okay? So as a result, whenever we have degeneracy in the problem, then we may have some problems. And I'm going to give you a more serious example now. And for that, I'm going to use an example. So the example that I'm going to show you, I already sent you by email. Okay, so the document should be in your email sort of inbox right now. All right, so can everybody see the example? So again, this is a PDF file that I just sent to you before class. So if you just go and check your emails, you should have this document in your folder right now. So here is the example. So we're maximizing 10x1 minus 57x2 minus 9x3 minus 24x4. That's the objective function. And then we have two constraints. Okay. Sorry, we have three constraints basically. And we also assume that all the variables are non-negative. Okay, so in this case, we have x1, x2, x3, and x4. Both of them are non-negative. And then what we do is we try to set up the simplex tableau. I'm going to define x5, x6, and x7 as the slack variables for the three constraints. And basically, if we just look at the first tableau, essentially this is what we have. Okay, so we have our three constraints. Our basic variables are x5, x6, and x7. Okay, which are the three slack variables. And the values of x5 and x6 are equal to 0. The value of x7 is equal to 1. Okay? So these are the right-hand sides. This is row 0, row 1, row 2, row 3, right? All right, so this is a maximization problem. So is this an optimal solution? No, so what should I be looking for? I should be looking for a non-basic variable with a negative coefficient, right? So in this case, there's only x1 basically. So x1 will be the entering variable. Okay. Now I'm going to apply the minimum ratio test. So what's the ratio for row 1? 0. So 0 divided by 0.5. I'm going to have 0 for this row. What's the ratio for row 2? 0. Again 0. For row 3, 1. It's equal to 1. So in this case, the minimum ratio is achieved by these two rows. Okay. So I can either pick x5 or x6. And what I'm going to do is I'm going to pick x5 as the leaving variable. Okay. So now, in the next solution, x1 replaces x5. So I have x1 here. Okay, x1 is the basic variable in row 1. And this is the second tableau. Okay? All right, so, we do a pivot and so on and so forth. And after you do that, you obtain this tableau right here. All right, so now, is this an optimal solution? No. So one thing that you should pay attention to is the following. The objective function value is 0. The objective function value is still 0, basically. Okay? So we decide to increase x1, but the best value x1 can take is equal to 0. Okay, so which means that the value of x1 in the next solution is 0, so which implies that nothing has changed basically. So this is just like going from tableau 2 to tableau 3 in the previous example. Okay? All right, so again, this is a maximization problem. Is this an optimal solution? No, it's not, so I can increase either x2 or x3, right? Both of them have negative coefficients in row 0. Okay? And let's go ahead and pick x2 because x2 has a larger negative coefficient. Okay, so then I'm going to look at the minimum ratio test. What's the ratio for row 1? Well, you should be careful. There's a negative entry here, so there's no ratio for row 1, basically, right? Okay, so for row 1, we just put a cross here, basically. All right, so what's the ratio for row 2? So it's 0 divided by 4, 0. And for row 3 rather, it's going to be 1 divided by 11. And the smallest ratio is achieved by row 2. So which means that the corresponding variable x6 will be the leaving variable, right? So x2 enters and x6 leaves. All right. So now x2 is the new basic variable in row 2, and x6 is non-basic. So we obtain this tableau. So once again, look at the objective function value, still 0. So we start with this one. we did one iteration, we did another iteration, and we haven't made any progress yet, right? So we're still actually looking at the same solution. But note that the only change is that the sort of labels of variables are changing, right? So some of them were basic here, they become non-basic, and some of the non-basic variables become non-basic. But they still exactly have the same values, okay? Now, once again, this is a maximization problem. Is this an optimal solution? No, so x3 has a negative coefficient, okay? So what's the ratio for row 1? So I have a positive entry here, so 0 divided by 0.5 is 0. What about row 2? Again, it's equal to 0, right? So we have the same problem here, and row 3 is not eligible for minimum ratio test because there's a negative entry. So again, we have a tie, okay? So I can pick either x1 or x2 as the leaving variable. So what I'm going to do is I'm going to pick x1 as the leaving variable, okay? So which means that x3 enters and x1 leaves, okay? So x3 will be the basic variable in the next solution. So I'm going to have x3, x2, and x7, right, in the next tableau. So indeed, if you look at the tableau, so we have x3, x2, and x7 as the basic variables. The objective function value is still 0, okay? So we haven't still made any progress. And is this an optimal solution? No, there are two non-basic variables, okay? So I'm going to pick x4 because that's the larger coefficient, okay? Then I'm going to look at the minimum ratio test again. What's the ratio for row 1? There's no ratio because there's negative entry. What's the ratio for row 2? 0 because there's a positive entry here. And for row 3, there's no ratio again because this entry is not positive, right? So there's only one ratio, which means that x2 will be the leaving variable. So x4 enters and x2 leaves. So x4 replaces x2 in the basis, right? In second row. So note that, again, we have a solution where the objective function value is 0. So we still haven't made any progress. Okay? Is this an optimal solution? No. Why not? So we have a negative entry here. Okay? So x5 enters. So I'm going to look at the ratios again. What's the ratio for row 1? 0. Ratio for row 2? 0. Ratio for row 3? No ratio. So we have two eligible leaving variables, x3 and x4. And I'm going to pick x3 as the leaving variable. Okay? So, which means that I'm going to pivot on this entry. So now my basic variables are x5, x4, and x7. Okay? And once again, the objective function is still 0. Okay? All right, is this an optimal solution? So x1 and x6 have negative coefficients, right? And x6 is a negative, larger negative coefficient. I'm going to enter x6. Now, what's the leaving variable? What's the ratio for row 1? No ratio. Row 2? 0. Row 3? No ratio. So there's only one leaving variable, which is x4. So I'm going to enter x6 and x4 leaves. And I have this tableau here. Okay? My basic variables are x5, x6, and x7. Okay? Well, so if I just go back, x5, x6, x7, pay attention to that. x5, x6, x7, right? I came back to where I started. This is not good, right? Okay? So, which means that if I keep doing the same things over and over again, I'm going to just sort of keep repeating myself. Okay? Without making any improvement at all. Okay? So, I mean, this is a serious problem with the simplex method. Okay? And the reason why this happens is the following. So, in this case, the same basic feasible solution is represented by, different choices of basic variables, basically. All of these choices of basic variables actually give you the same corner points, okay? So the problem is that, of course, I cannot draw this in four-dimensional picture. But if we were able to draw this in 4 dimensions, then we would see that the same corner point is represented by the intersection of many different constraints, basically, okay? So as a result of which, whenever we sort of change the basic variables, we're still looking at the same corner point. So in this case, 1, 2, 3, and on the second page, 4, 5, 6. So these 6 different choices of basic variables give me still the same corner points. Okay? So which means that, if I keep doing the same things over and over again, so I'm going to keep repeating myself. Okay? And without making any progress at all. That's the sort of scary part. Okay? So the objective function value was 0, and the objective function value is still 0. So we didn't make any progress at all. We just sort of kept sort of doing some operations without changing anything at all. Okay?
Bu başa dönene kadar kaç tane tablo çizdiysek o kadar tane kesişim olacağından dolayı yani kaç tane liner kesişimini söyleyebiliriz.
Well, okay, you can say it in this way. There are at least 6 different basic variables. At least 6. Okay? There may be more than that, but you already have 6 here. Okay? There may be more than that. The same is true in our example as well. We have at least 2 representations of the same corner point. Okay? So in this case, we have at least 6. So this is known as cycling. Okay? So basically, the simplex method starts with a certain basic feasible solution. It does a bunch of operations, and it comes back to the same basic feasible solution again. Okay? So which means that you start at a certain point, you do certain sort of operations, and you come back to where you started. Okay? And the problem is that, so this is something that you have to handle carefully, because if you don't, then you're not going to make any progress at all for your problem. Does everybody see that? Okay? So I think we're out of time right now, but essentially what I'm going to do is, I'm going to show you that in the next class, if we apply the simplex method carefully, okay, then I'm going to show you that this will never happen. Okay? So what I mean by carefully is the following. So here, whenever we had a choice for the entering and leaving variables, we picked them arbitrarily. Okay? We didn't apply any rules. So we just picked whichever we liked. So in the next class, I'm going to show you that if we actually pick them carefully, okay, if we apply a certain rule, then we're going to see that cycling never happens. Okay, so we're going to actually, in next class, discuss that there's a way to prevent cycling in simplex method. Okay? Any questions? Well, I'll see you next time.